Hello and welcome to my YouTube channel. Today I will present an article, Global Warming. Part 2. Don't forget to like and subscribe. Dear friends, last time I reported on the increase of carbon dioxide in the atmosphere. This is a representative graphic, which I did not put by mistake in the previous video, my apologies. In it, you can see, on the horizontal axis is time, the evolution of carbon dioxide concentration in the atmosphere over the last 10,000 years. See how sharp the rise has been in the last couple of hundred years? It is due to the burning of fossil fuels, as I have argued. Today we continue our journey by presenting the greenhouse effect. It is very important to understand the details of this greenhouse effect so that later, to see how much carbon dioxide contributes to global warming, we'll use a lot of the stuff discussed here. It is also interesting to understand how the atmosphere keeps the Earth warm and how important the role of carbon dioxide is. For clarity, we will refer to the greenhouse effect as the effect whereby atmosphere has kept the Earth warm for billions of years and global warming as additional increase in the Earth's temperature due to the burning of fossil fuels and the release of industrial-era gases into the atmosphere. At the end of this episode, we address some myths and questions. In the next episode, with what we've learned here, we're going to dot the I's, we're going to calculate the temperature rise. In the case of global warming, we didn't do it all in one episode, as there was a lot of material. Before we begin, notice the bottom bar? To my surprise, I received the Best YouTube Creator 2023 award. The Webstock Awards. Despite the fact that this channel doesn't have millions of subscribers, you, the audience, and the jury probably appreciated the content. Thank you to everyone who voted for me. Let's get started. Earth without atmosphere, -18 degrees Celsius. It's cold in space. If you put an object in outer space, we'll be surrounded by background radiation, the light that appeared after the Big Bang explosion and has now reached the microwave field. As in a microwave oven, the background radiation will heat it up to the temperature. Its temperature, which is just 2.73 Kelvin above absolute zero, -270 degrees Celsius. But the Earth has two other sources of heat, the Sun and the Earth's, core heated to thousands of degrees Celsius. From the Sun, the Earth receives an average of 173,000 terawatts of power, i.e. 173 million billion watts. Reminder, 1 watt is 1 joule per second. From the Earth's core, the Earth's surface receives an average of 47 terawatts, or several thousand times less. This thermal energy of the core turns out to be about 20 times less than that induced by global warming, which is why we'll neglect it. Whether the Earth was further from the Sun, or an orphan planet without a star, was another matter. What is the average energy the Earth's surface receives from the Sun? As the Sun lights only half the Earth, we divide the 173,000 terawatts of energy to half the Earth's total surface area. We obtain that, on average, during the day, the Earth receives about 680 W per every square meter, in equatorial areas more, towards the poles much less. If we take into account a whole day, and therefore night, energy, the average received is half of this value, i.e. 340 W/m2, here you have to change the picture. Some of the Sun's light, about 30%, is reflected back into space, which means that the effective energy density received by the Earth is 0.7 times 340, or about 240 W/m2. Interestingly, based on this value, we can estimate the Earth's temperature in the absence of an atmosphere. Thus, in thermal equilibrium and without atmosphere, the Earth's surface must radiate the same energy back, i.e., 240 W/m2. But this is thermal radiation, emitted by a heated body, as does the human body, which is also heated. And this thermal radiation, for the temperatures we are talking about, is emitted mainly in the infrared. That's why night cameras use infrared sensors. The higher the body temperature, the more infrared radiation is emitted. This relationship is called the Stefan-Boltzmann formula. It tells us that the energy density emitted by A unit area is sigma multiplied by T to the fourth power, where sigma is the Stefan-Boltzmann constant. The formula is used in infrared thermometers, which measure the temperature of a surface from a distance. They focus infrared radiation emitted by a small area of skin onto a sensor. The laser beam that some devices have has no room to measure, it is only to identify the area on the skin from which the temperature is taken. Knowing the surface area of the skin and measuring the strength of the radiation with the sensor, calculate the temperature of the emitting surface using the Stefan-Boltzmann formula. Simple, right? Let's do a similar exercise. Estimate the Earth's surface temperature in the absence of atmosphere. We know what it is. Area of the Earth, and we know the energy density it would emit in equilibrium, 240 W per m2 of surface area. We have the Stefan-Boltzmann equation and we need to find out the temperature, therefore. We change the terms between them. Here you put the picture because mine looks bad. Now we substitute in the formula and find the temperature. We get that, in the absence of an atmosphere, the Earth's surface would. It was supposed to be -18 degrees Celsius. Good luck. And obviously, it's warmer than that on Earth. The greenhouse effect or the Earth's blanket. Fortunately, on Earth there are, on average, more than -18 degrees Celsius. And that's due to the atmosphere, which works like a blanket, to quote physicist Lawrence Krauss, or as a greenhouse effect, to use a more common term. Have you seen how the duvet is warm on the inside and cold on the outside? So is the atmosphere. It is warm on the inside, the side facing the Earth where we live, and cold on the outside. Thus, the outer layers of the atmosphere have temperatures of -50 degrees Celsius. And the inner layers have temperatures equal to those at the Earth's surface. This way, the atmosphere keeps us warm like a quilt. Here is a draft model. I drew the Earth's atmosphere, simplified, as a single layer. It has several layers. We see how the light coming from the sun, being in the visible spectrum, passes through the atmosphere and reaches the Earth, heating it up. The Earth, when heated, emits thermal radiation in the infrared range. This radiation is absorbed by the Earth's atmosphere, which then re-emits it in two directions. To outer space and the Earth's surface. Receiving back some of the emitted radiation, the Earth's surface is additionally warming. Here's why it's hot on the Earth's surface. The above effect is also called the greenhouse effect because is similar to the way the air becomes warm in a greenhouse. Here the sunlight shines through the glass above the greenhouse and warms the air inside. The heat in the greenhouse does not can get out because the windows are closed. This way, the temperature in the greenhouse rises, which is good for the plants. Between the two models, the greenhouse effect and the duvet, probably more suitable, is the second. But it's just a name. The question is whether the phenomenon described above is correct and whether the Earth's temperature is rising due to the atmosphere. To do this, we would have to measure the temperature of planet Earth, as we have seen that body temperature is measured, i.e. with an infrared thermometer. Measuring the Earth with a thermometer. What do you have, me, a thermometer for Earth? Just kidding. Such a thermometer exists, and he measured not only the temperature, but the entire infrared spectrum of the atmosphere. Before I show you the result, I feel obliged to present an optical spectrum, emitted by a body heated to higher and higher temperatures, so we understand what we're talking about. There he is. On the horizontal axis is the wavelength of the light emitted and on the vertical axis, the intensity. This is what the spectrum of a body looks like. Heated. For a single temperature, we see a curve that peaks in the infrared range, a few micrometers, and at the ends, the intensity decreases. The curve describes the blackbody radiation, which means, if a body is black, it emits light when heated. That's why the burning candle is bright, even if it's black when extinguished. We also see on the curve how the higher the temperature, the higher the total intensity of the curve, which means that the infrared radiation emitted by the body is more. This is the Stefan-Boltzmann relation, already used above. Each curve is modeled with a formula, thanks to physicist Max Planck, that tells us what the temperature is. Here is now the promised spectrum, i.e., the radiation emitted from the top. The atmosphere. In this case, the radiation was measured by an aircraft 20 kilometers above the Earth, to the right of the South Pole, over Antarctica. On the horizontal axis is the wavelength of the radiation, at the top, expressed in micrometers. The same horizontal axis is also expressed in wave numbers, part of the down, in cm-1, which is another expression of wavelength. On the vertical axis, we have the radiation intensity. For clarity, researchers have already modeled the curve with Planck's known formula, so we can read directly what the temperature represents. If we zoom in, we see that, for the most part, the curve describes a body heated to a temperature of about 268 Kelvin, just a few degrees Celsius below zero. This is the radiation that escapes into space directly from the Antarctic surface, where the temperature is indeed just below freezing. This radiation has not been absorbed by the atmosphere, which is why it reaches space. The interesting part is in the infrared field, where the radiation wave number is between 600 and 700 cm-1. Here we see a sudden drop, describing a body heated to 225 Kelvin, or about -45 degrees Celsius. What can it be? The answer is this part of the spectrum represents the infrared radiation emitted by the atmosphere, in its upper part. Here, in the stratosphere, the temperature of its upper layers is about -40 degrees Celsius. We see how, compared to the rest of the graph, which depicted the radiation emitted by the Earth that escapes into space, here the intensity is low. This means that in the range 600-700 cm1, the radiation emitted by the Earth's heated surface has been almost entirely absorbed by the atmosphere. Only thermal radiation from the stratosphere layer at 20 kilometers is visible. To convince ourselves of the interpretation, let's take another look at a spectrum of the radiation emitted by the atmosphere, but from this time not from space, but measured by a ground-based spectrometer looking up into the atmosphere. We see here how between 600 and 700 cm1 the intensity is really maximum, and otherwise quite small. That is, the atmosphere has indeed absorbed radiation in this interval, 600 and 700 cm1, and now partially re-emits it towards the Earth's surface. That's what warms us up. Let's see for ourselves by reading the temperature associated with this radiation. It is about 270 Kelvin, which is a few degrees below zero, as much as it is the temperature at the bottom of the atmosphere, at the surface of Antarctica, where the measurement took place. In other parts of the world, where it's warmer, this temperature will be higher. If we superimpose the two graphs on top of each other, we understand the essence of the global warming mechanism. At its outer surface, its temperature, given by thermal radiation between 600 and 700 cm1, is about -45 degrees Celsius. At the bottom the temperature is higher, equal to that at the planet's surface. This is the duvet I was talking about, cool on the inside and warm on the outside. We also note that this effect is responsible for only part of the radiation, infrared radiation, more specifically between 600 and 700 centimeters -1. This is where the Earth's thermal radiation is absorbed by the atmosphere, radiation that is then emitted into space, less, and to the Earth's surface, more. Much. But what does the radiation emitted by the Earth absorb into the atmosphere? What molecules do this? Molecules of the atmosphere. Molecules absorb light. That's why our hand, also made of molecules, is heated by fire. The question is, which molecules in the atmosphere absorb the infrared radiation emitted by the Earth's heated surface? To answer that, we need to understand, in a nutshell, how light is absorbed by molecules. Molecules, made up of a few atoms, vibrate. When the frequency of light reaching the molecule is equal to with the frequency of a vibrational mode, resonance occurs and light is absorbed by the molecule. Molecules with two atoms vibrate in the direction of the two atoms. When the two atoms are identical, this vibration is fast, so only light that has a very high frequency, even in the ultraviolet range, will be absorbed. Molecules with two or more different atoms have other modes of vibration. If there are three atoms, the molecule can also bend in a perpendicular direction on its axis. The vibration frequency is lower, reaching the infrared range. Let's see, what is the atmosphere made of? 77 to 78% nitrogen, has two identical atoms, does not absorb infrared. Oxygen 20 to 21% has two identical atoms, off the list. Argon 1%, one atom, no infrared absorption. Wow! There's less than 1% of molecules left that can absorb infrared. First on the list, water vapor, with an average of 0.4% and large variations, has three different atoms, hydrogen and oxygen, so it can absorb infrared radiation. Next is carbon dioxide, 0.04% concentration, has three different atoms, carbon and oxygen, neon, helium, no, methane, yes, even though it has an extremely low concentration of 0.00015%, the coefficient methane uptake is high. And, pretty much, they were. We pause to realize the importance of the moment. We have three molecules on the list, water, carbon dioxide and methane, whose concentration in the atmosphere is less than 1%. Yet they are the gases that keep us warm on Earth. Without them, it would be -18 degrees Celsius on Earth. Few, but important. They are called greenhouse gases. Due to lack of space and time, we leave methane aside for the moment and discuss water and carbon dioxide. We can check whether they really contribute to the Earth's warming by looking at their absorption spectra in the 600-700 cm1 band. Here is the spectrum. On the horizontal axis is the wave number, bottom, and on the vertical axis, the intensity. What do we see? That both molecules absorb radiation in the range 600-700 cm1, radiation emitted by Earth warmed, let's remember, so both make the atmosphere's quilt work. If we look at the red curve, corresponding to carbon dioxide, we also read on the right of the curve the absorption coefficient, approximately 10 to the power of -2, 10 to the power of -3 m to the power of -1 for our range of interest. The inverse of this number is the average distance the radiation travels before it is fully absorbed. This gives us 100,1000 meters. This means that the infrared radiation in the area of interest 600-700 cm1 travels through the air for a few kilometers and is then absorbed. As the densest part of the atmosphere is several tens of kilometers high, we conclude that all radiation in the range of interest 600-700 cm1 emitted by the Earth's surface is absorbed by the atmosphere. That's what the spectroscopic measurements at 20 kilometers height were telling us. It all makes sense. We also see how the water spectrum is made up of many separate absorption lines. This is a first problem. Major challenge for researchers, the spectrum is difficult to model with analytical formulas. In addition, the concentration of water vapor depends a lot on location and temperature, from 0.01% in Arctic areas to over 2% in some warm areas. In addition, the natural water cycle makes a water molecule stay for an average of 10 days in the atmosphere. Therefore, water behavior is one of the biggest sources of uncertainty in climate modeling. Today, it is difficult to estimate precisely how much water we owe, that the atmosphere keeps us warm, and how much carbon dioxide. In general, depending on weather conditions, the water contribution is estimated to be between 40 and 60%, carbon dioxide between 20 and 30%, and of methane below 10%. To this is added the contribution of ozone and the variable contribution of clouds. Conclusions. Here we are at the end of this episode. We've identified who helped us keep the cold off this planet. Atmosphere. Let's take another look at the outline of the greenhouse effect, the way the blanket of atmosphere keeps us warm. We have identified 3 of the molecules in the atmosphere that absorb the radiation emitted by the warming Earth: water, carbon dioxide, and methane. By re-emitting some of this radiation back to Earth, the Earth is warmer at its surface. Personal opinion? The fact that it's not cold on Earth, like on Mars, nor very hot, as on Venus, is due to a mismatch in the composition of the atmosphere. It's not obvious that the planets of the universe have the chance that Earth has had. I say, let's realize that we are in a big universe that we need to understand if we want to live comfortably in it. Myths. Carbon dioxide is only 0.04% of the atmosphere. It's very little. It has no way of affecting the atmosphere and causing global warming. False. Although I have only talked about the greenhouse effect here, not global warming, I should have addressed this myth, because it can be answered right now. It has outraged me ever since. I've heard it rolled around in the media. First of all, it is philosophically false. If a thing is small, doesn't mean it's not important. If someone gives us to take 0.04% arsenic, do we take? No, no way. Same with carbon dioxide. Firstly, even at such a low concentration, it contributes 1/4 of the Earth's normal warming effect. Without it and without water, which are also below 1%, the Earth would have averaged -18 degrees. BRRRR. Even with these low concentrations, we owe it to the two gases that we don't get cold. Already having an estimated 1/4 of the Earth's total warming influence, it is no wonder that a doubling of carbon dioxide concentration could have a real and visible effect in raising temperatures. We'll see in the next episode. Here we are at the end of today's episode on the greenhouse effect. Next time we'll use what we found out today to see how much the Earth's average temperature is rising due to the sharp increase in carbon dioxide in the industrial age. Wolfram Alpha again, Spectra again, physics on bread. Until next time, please subscribe if you haven't already done so by clicking now this subscribe button. Thank you to those who support us on Patreon and here by becoming channel members. I'm Christian Prajura and I wish you all the best. Bye.